Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 51 in the series, Simplifying Rational Expressions. We've already seen at least one form of how to simplify rational expressions in the form of canceling monomial factors. For example, in the following polynomial, one could factor the GCF out of the top and cancel it with the denominator. In this case, it cancels completely, and we just get the remaining factor in the numerator. Of course, we have to keep in mind that x cannot be equal to 0 in this case, even though with this canceled term, it doesn't appear to pose much of a problem. This was also the pattern of things when we dealt with proper factoring and separating a polynomial into two factors and canceling, not just the greatest common factor. But in either case, this kind of factoring and canceling resembles how we simplify fractions. So for example, if I wanted to simplify a fraction like 12/4, I could see 12 as 4 times 3 and then cancel these factors, leaving me only the 3. And we had a property of fractions that says if I have some factor in the numerator and some factor in the denominator that match, then they cancel to 1. And you just get the remaining terms, in this case b and c, left over as a new fraction. Sometimes c is equal to 1, and this is a whole number, but in general, you get a simplified fraction. So as usual, our general guide is to use the patterns from the cancellation of fractions, or from the arithmetic and the algebra of fractions, to help us see the right way of doing things when it comes to quotients of polynomials, the rational functions. Here's another example of one of those patterns of cancellation from fractions. If you have a product of two fractions, you can do top to top and bottom to bottom and then cancel. But it's in general simpler to cancel before you multiply things out, right? If you see things when written as a product, factors matching on the top and bottom, they can cancel to 1 in this sense too. We really just reorganize the multiplication that's going on here until we get a times its reciprocal before we do anything else. This is still c over b. Another might be if we were dividing by a fraction. When I flip it and multiply, if there's some cancellation of terms here, then we'll also get cancellation in the sense that we don't really have to multiply things out. We don't have to take this all the way through to a, c, d, and then b, d, a, and then cancel. We can cancel right here. It becomes clearer when you rewrite this as multiplication, because then you can see who's really on top and who's really on the bottom. So our main technique for dealing with rational functions is going to be to factor every polynomial in that rational function. This is why it was so important for you to really get good at factoring polynomials, because some of these problems, a single problem might in fact require you to factor 4 or more polynomials. So this is going to be just a standard move that we do at the beginning of the problem. We're going to have to factor the polynomials and then rewrite division as multiplication by a reciprocal and then cancel our terms here. We'll also later on look at what we need to do to add two rational functions together, and that will also call back to the pattern of addition and subtraction, getting like bases from the addition and subtraction of fractions. In any case, almost all of the maneuvers that we're going to do with simplifying or performing some arithmetic on rational functions is going to be a combination of factoring polynomials and the rules for the arithmetic of fractions. That's it. Those are going to be our two main moves. There is rarely going to be anything else involved when we deal with rational functions. So let me give you an example. Here is the multiplication of two rational functions. I have x squared plus 4x plus 4 as the numerator here over x squared minus 4 times x squared minus 5x plus 6 over x squared minus 9. And I want to multiply these two rationals together, but before I start foiling all of this stuff out and make a real mess of things, what I should do is I should factor first. We should factor the top polynomial, which is x plus 2 squared, and the bottom polynomial here, which is x plus 2 times x minus 2, difference of squares. Likewise, over here, I have x minus 3 times x minus 2 on the numerator, and x minus 3 and x plus 3 in the denominator. Notice these x minus 2's cancel across from each other. The x plus 2's cancel up and down right here. Same with the x minus 3's. And so really, when all of this cancellation is done, there's very little multiplication to do. there's not really any non-trivial multiplication to do, because since everything canceled to 1 here, we have 1 times x plus 2, and everything canceled on the bottom to 1 except for x plus 3. So we have an x plus 3 on the bottom, and that's it. There's nothing else to do with this one because these aren't like terms. You can't simplify this any further, so that would be your answer. Let's look at another example that has division involved. So we would start with taking this whole expression. We have x squared plus 9x plus 18 over x squared minus 2x minus 15. And then on the other side, we got 3x squared plus 19x plus 6. We've got x squared plus 4x plus 3. We have to factor all 4 of these and then reset this up as multiplication. So let's factor first. This top one is x plus 6 times x plus 3. This bottom one is x minus 5 times x plus 3. Then this one, I've omitted the work, but we can check by foiling, right, that this is going to be 3x plus 1 times x plus 6, right? We'd get a middle term of 18x plus 1x is 19x. And then our first term would be 3x squared, our last term would be 6, so this is the right factorization. Then this bottom one is a little easier. This is x plus 3 times x plus 1. Now, before we can see what cancels, we need to rewrite division as multiplication. And when we do that, whatever's on the top and whatever's on the bottom will cancel. So that's the x plus 6's, that's these two x plus 3's, and that's all that cancels. So we combine the terms that are left, and we write this as x plus 3 times x plus 1 over x minus 5 times 3x plus 1. So you should know how to FOIL these out and get two expanded polynomials on the top and bottom, but I'm just going to continue on. So another simplification that you might see with rational functions is the way that a negative sign can sometimes be absorbed into a difference. Let's see how that looks. So what we want to notice here is that I had a negative sign on the top. This might have been out front, or it might have been on the bottom. It doesn't really matter where this negative sign was. There's a times minus 1 involved. And notice that I have a difference, a minus b. A very classic way of sort of omitting one of these symbols and making things a little bit simpler in terms of, an economical use of symbols is to absorb that negative into this difference by switching its direction. You might be able to see that that's how things should be just by looking at it, but let's break it down to make sure this pattern makes sense. But just to summarize, we can get rid of a negative sign by changing the order of subtraction in a factor if that factor involves some kind of subtraction. To see why this should be the case, remember that if you distributed a minus into a difference, it changes who has the negative sign, which, because addition is commutative, we could rewrite. And then in this case, getting rid of this minus 1 could be seen as multiplying it by minus 1. If I do this on the top and the bottom, nothing's changed about the value of our expression, but the bottom is going to look like minus 1 times a minus b, which we just saw was b minus a. So the top turns into a positive 1 while the bottom switches. Okay, here is your praxis. These are your practical exercises for the day. I want you to simplify the following expressions. So see if you can pause the video at this time and work these out using the above notes as an example. Give each one of these a shot. Okay, let's see how you did. So the first step in this one would be to factor out a greatest common factor. You could just divide this into each one. That's another way of looking at things. But factoring out the greatest common factor is probably a good idea because it has this advantage of leaving you in a factored state at the end, which is nice. If I take 48 and 24, they have a 24 I could take out of both of them. The smallest x is an x squared. I take that out too. And then the smallest y is a y squared. I take that out too. What's left when I do that? Well, 48 divided by 24 is 2. X squared divided by x squared goes away. And y cubed divided by y squared just becomes a single y. In my other term, there's a minus sign. 24 divided by 24 is 1. X cubed divided by x squared is just x. And then y squared divided by y squared is just 1. So the y's disappear here. Now, I could divide this lower term, 12x squared y squared, into the numerator. 12 goes into 24 twice, and the rest of them cancel to 1, leaving me with just 2 times 2y minus x. Okay, here's our next one. We've got x squared minus 4 over x cubed plus 3x squared, x cubed plus x squared plus x plus 1 times x squared plus 1 over x squared minus 4x plus 4. So the one of these that I think is kind of tricky to factor is this one, unless you remember how to factor by grouping. If you see a cube with 4 terms, you should try splitting it in half and pulling out a greatest common factor from each half. And if we do that, we see that we have matching. We have x plus 1 in 2 places. This lets me divide it out, and then I get an x squared, and also a 1. When I divide this term, it technically has a 1 coefficient here, so a 1 must come out with it. Couldn't just be x squared, or you wouldn't get this when you FOILed it back out again. And we pull that x plus 1 outside. So we could factor this cubic using factoring by grouping in this way, and the rest of them factor pretty normally. This is difference of squares, this is a perfect square, and this one, x squared plus 1, unless we're talking about factoring over the complex numbers, this doesn't factor. This has to stay prime. So, but that's okay, because look on the bottom here, we have an x squared plus 1 to match. That cancels to 1, and so does this x minus 2 over x minus 2, and then we just have a x plus 1 and an x minus 2 on the bottom, and this x plus 2 remaining on the top. We could FOIL that out if you like to get an expanded polynomial. Either one of these are correct answers. Finally, let's look at this division problem. The first thing I would do is factor everything. So let's write this as factors. Plus 2 minus 8, right, turns into an x plus 4 and an x minus 2. I would expand to give this. This is difference of squares again, so x minus 4, x plus 4. Another difference of squares, x minus 6, x plus 6. And this one, we need factors of 24. There's a minus sign, and then we need another minus sign to give me a positive. So we need factors of 24 that sum to be 10. That's 6 and 4. So we rewrite this as multiplication. The vertical stuff cancels because you have top and bottom matching. And then this x minus 4 cancels across. And this just leaves me with x minus 2 over x plus 6. And that's going to be it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.